Hi, I'm Bill Lundgren. In this video demonstration, I'm going to illustrate the simplicity of building applications and then having the compiler build a version for target hardware. In this demonstration, my target is going to be simply the computer that I'm running on. So let's get started. The first thing I'm going to do is to invoke the Gedae development environment, so we're starting that up now. Gedae has a canvas for block diagram editing. In this case, we just have a text field on the canvas. What we're going to do is not to use a block diagram for this initial demonstration, but we're going to use an idea function. Gedae has an FG libraries where all the components of your application are stored. In the boxes directory, all the text code for your application is stored. So I'm going to create my idea function in the users directory, and then Bill HG for Hello Galaxy, and then I'm going to call it run Hello Galaxy .I for the extension for the idea language. And so Gedae opens up an editor. In this case it's Emacs, and I can use that in order to create my application. In the first phase of this demonstration, I'm going to create a very simple demonstration to illustrate the streaming of data. So I've created a stream of floats. I'm going to call it Y0, and I'm going to set it equal to normal, so I'm invoking a function, and I just need a seed for it, so I'll call it 3452, and any integer will do for the seed. So now what I have done is I have a kernel which is going to be a source kernel, which means that it doesn't need any data on the input in order for it to run, and so every time there is an opportunity to run, it will run. Of course, it's all constrained by the data flow and the other functions in the system, and in this case I'm going to simply put a line of code that's going to print out the value of my variable, and what we should see is we should see a stream of these coming out into our terminal over here once we run this. Now so if I save that, then you'll see that the compiler loads it into the development environment, and so there's our print debug statement, and if I run it, then there's my application running. Notice that it normal runs, print debug, normal, print debug, and so on. And we can actually see that by looking at the schedule. So this is the kernel. Kernels are a different type of function, and those are used to encapsulate C code. And if I open this up, then you can see the actual code, and again there are other demonstrations and lectures that describe this code. But this code is a parameter input, and it puts a stream of data out, and so it's a source kernel, and it can run forever as long as the application is enabled. So I'll stop this. I'll close that. And the other thing that I want to do, what I want to do is to view the schedule. And when I view the schedule, you see there are two functions in the schedule. It calls the SF normal function, then it calls the SF print debug function, then it repeats. It keeps repeating. And that's because this SF normal box is a source box. So that's an illustration of how to build an application in Gedae. In the second phase of the demonstration, we're going to increase the complexity of the application a bit. The editor is still up here, and what we'll do is we'll delete this print debug line, and what we're going to do is illustrate a couple more of the features of the idea language. So we're creating a range variable of size 2, and that has two values. It takes on two values, 0 and 1. And so the next thing we're going to do is convert our stream of scalars into a stream of vectors. So we'll do y1 bracket. Notice that we're using a square bracket for the array index, in this case a vector. and we're going to set that equal to y0 of open paren c close paren semicolon. So the open paren close paren, the parenthesis, represent a scalar stream in this case. So a stream of data, it's a stream index, and we're taking two tokens, two scalar tokens off the stream and creating one vector token. And so the next thing we're going to do is make it a matrix, and so we'll add another range variable with r set to 3, and we're going to create a matrix with r rows and c columns, and we're going to set that equal to y1 c, but we're going to use the parens for the r, so we're going to take 3 vectors off the stream and create this matrix. And finally, what we want to do is to display the data in an image display, so we'll call pass it to the function image and save it, and you'll see that it will update. So I hadn't terminated the graph, so it didn't update. So now I've terminated and updated automatically. And so the next step is to simply run it. And so there we have our application running, and now we've created a matrix of data, and we're displaying an image display. In the third and final phase of our demonstration, we're going to create a version that will run on the target hardware independent of the development environment. It's actually very straightforward. We're doing a very simple thing, just running it in a single task, no parallelization. So the first thing is I will terminate the graph, and then I'm going to go to the Tools menu and to the Implementation Control. The Implementation Control gives you lots of capability for defining how the application is going to be implemented on the target. We're only going to do one thing. We're going to select the run on target. You can partition the functionality. You can take those partitions and map them to different processors and so on. Look at the transfers and set the parameters or choose the transfer methods. But we're doing the very simple thing, just running on the target hardware. And when we do that, we simply go back to the development environment and select the Run button, and the compiler goes off and builds the application. Here you can see it is now running. So what I'll do is I'll stop the application or terminate the application, and then I'll exit the development environment. And it's asking me if I want to save the group files, and you can see I've run this previously, so there is a settings called target. The main thing to take away here is that much of the information about the applications and how it gets implemented are stored in separate files so that the code doesn't get cluttered. The compiler takes the individual components, integrates them together, and creates a monolithic code. So we're going to exit our editor as well here. And Gedae creates these in a very specific location, in this case the embedded directory. And then in the embedded directory there's a run hello galaxy 1 directory. And if I do an ls of exec -star, then you see there's a build and an exec host and a .c file. And so those the exec-host is the executable. So I will simply invoke the exec host, and there we have the application running outside of the development environment. So building applications in Gedae and then targeting those applications on a variety of hardware is very simple and straightforward. That's a very good development environment. It's easy to use, and it's also a high-level language that's easy to write complex applications in quite quickly. One of the things you should take note of this is as we went through the 3 phases, the first one, the first 2 were the longest, and that was developing the application. The effort required to actually build the software, the application version that runs on the target hardware, was the shortest of the 3 phases, and that's typical of the development using Gedae. Thank you very much for listening to this video, and if you have any questions, please send an email to support support@gedae.com. That's support@gedae.com. Thank you.